In today's steel structural construction industry uses different steel shapes. Each steel shape has its unique structural behavior and used at appropriate locations in the structural model in order to achieve the strength. Steel is rolled to a required shape during manufacturing accordingly to its requirements. There are many different types of shapes available in steel sections. However, there are typically generally used I section, T section, C section, L section, and hollow sections, steel bars, sheets in the structural industry. Let's discuss about these sections. Now, for I section is also called as universal beam. This I section, also called as universal beam. So this has been used generally where the bending moment is predominant, like bridges, industrial structures, like columns, beams, and gantry girders, like that. Similarly, for even T sections is used for load-bearing beams. For channel sections, also called as a C section because of the shape, and angle section is also called as L section. These both are widely used in the steel structural industry in many places, like bracing members, even leg members, and redundant members, appropriate places in the structure. For circular hollow sections and square hollow sections, normally used where the movements are multiple direction for that particular members. That means the member is subjected the forces in both the directions, like seismic forces or wind forces, like that. So in those conditions, normally we use these hollow circular sections or hollow square sections or rectangular sections. And steel bars and sheets, we know which has been used many places, depends upon the requirements. Now let's discuss about the internal and outstand elements. Why do we need to know about these elements? Because based on these elements length and width and thickness, the section has been classified as class 1, class 2, class 3, class 4. Similarly is like a plastic, compact, semi-compact and slender sections. These will be important in order to estimate the load carrying capacity of that particular member. So now what is the internal element are to be considered to be supported along two edges. This element also called as stiffened element. That means if any element, for example this element, if you talk about this element, is actually subjected by this flange and this flange. So this is called as internal element. Internal element. Now if you talk about the outstand element, is actually a outstand element are considered to be supported along one edge and free on the other edge. Free on the other edge. This side is free, this side is supported by this web. So this element is called as outstand element. So when it comes to the composite section, for example you take this section, okay. So now these two webs are considered, so up to this section is called as internal element. What is the outstand element over here? This portion is called as outstand element. Outstand element. So now come to this square or rectangular hollow sections. What are the internal elements? See, we already say that the internal element is nothing but it's supported along two edges. For example, this element, you take this element. This is supported by this one and this one. So this also called as internal element. Now again if you talk about this element, this also supported by this and this. So this also will be called as a internal element. So this is called internal. How this can be used? Because if you see in general, this is called, let's say here, this is called actually B and this is called actually a thickness of the member. So based on this B by T, we can able to find out what is the particular section classification. How these classifications has been defined? As I said, the sections has been defined class 1, class 2, class 3, class 4. Scientifically or engineeringly, this can be classified as plastic, compact, semi-compact, slender based on the behavior of the element. Now let's discuss about what is the definition or what is these classes will behave. If you look into the stress strain curve, any member when you tested laboratorily, based on the plastic, compact, semi-compact and slender, the section behave like this. So what is that? We can go one by one. For the plastic section, it will develop a full plastic movement MP. That means this is the MP. Full plastic movement will be developed. Let's say, for example, a member, if you start bending a beam, it will form a plastic hinge initially, right? If you keep bending and continue to bending, the hinge will maintain a certain level of strength until complete failure mechanism is formed, is called as a plastic section. Until complete failure mechanism. This is called as a plastic section. Plastic section. Now, compact section. It can develop their plastic moment MP. This also will develop the plastic moment. What is that? Compact section. But allow only limited amount of rotation. The limited amount of the rotation will be up to certain here. That means local buckling of that element will prevent the required rotation. So that means the local buckling of the element will be prevent. So this section is called as a compact section. Now come back to the semi-compact section. The semi-compact section is nothing but local buckling prevents to develop the plastic moment MP. It can only develop yield moment My. It won't develop the MP. Before even touching the MP, the local buckling will prevent in order to achieve the MP, but at least will go up to the yield point of the member. This is called semi-compact section. Now come to the slender section. The slender section is nothing but the section are those in which yield in the extreme fibers cannot be attained because of premature local buckling in the elastic range. That means it's not even reaching the elastic range and before it actually fails. That is not a yield moment as well, is below the yield moment. That means, let's say for example, we'll take a I section, simple I section, okay? So if you can see the I section, this section even before it reaches to the yield point, it actually slightly will undergo the buckling of the, for example, web element. So in reality, in the calculations, the complete sectional properties will not be available because this portion already buckled, locally buckled before even it reaches to the yield point. So you will be deducting this portion of the section. So that means the total cross-sectional properties minus this cross-sectional property will be taken into consideration. When it has been deducted, the partial section properties has been taken out and limited section properties are available for that particular section. If you multiply it by the stress, you will be getting less moment capacity compared to the semi-compact, compact and plastic. So in a particular section, if it is a slender, the less moment, and go ups, plastic is a higher moment capacity will be there. Now let's look into this section properties definitions. What are the definitions we have? So this is plastic, compact, and this one is semi-compact, and this one is slender sections. So now let's go to the section classifications. Class 1 plastic can develop plastic hinge with the rotation capacity required for plastic analysis without any reduction of resistance. So we already discussed there is a internal or outstand element B by T is less than beta 1. So we'll discuss what is the beta 1 in the next slide. Similarly, for compact section or class 2 section can develop the plastic moment resistance but limited rotation capacity due to the local buckling, which also we discussed. For class 3 semi-compact can only develop elastic distribution where the extreme fiber stresses can reach yield, but local buckling prevents further development of the full plastic moment resistance. So this is called class 3 section. The slender section develops the local buckling before attainment of the yield. That means we already discussed the local buckling will develop even before it reaches to the yield point of the section. Now, so what is this beta 1 and beta 2 and beta 3? So IS 800 code in table 2 class 3.7.2 and 3.7.4 has been given more in detail about section classifications based on outstand element or internal element. So if you can see that code book, you can see there is a outstand element and internal element, a web element or angle sections and all those things. So now there is the plastic section beta 1 is given, compact section beta 2 is given, and semi-compact beta 3 is given. So beyond this limit is called as a slenderness, slender columns, which is slender sections, which is called as a class 4 sections as well. So B by T, for example, if you take this example, B by T is less than or equal to 9.4 epsilon. The epsilon is nothing but 250 by Fy with square root of 250 by Fy. So based on that, the limiting value of the beta 1, beta 2, beta 3 has been given, and we need to apply in order to achieve the section classifications. Once you know the section classifications, you multiply appropriate section properties in order to get the strength and moment of the particular section. So we'll see more in detail in the examples. So now mechanical properties of the steel. So we discussed the section properties based on the classification of the section properties, plastic section properties or elastic section properties or net section properties where the slender section will be calculated. Now come to the mechanical properties of the steel. Based on the thickness of the member, we can able to identify for each grade what is the yield stress. You see, this is the thickness of the member. If the thickness of the member less than 20 mm and grade of the steel E250, the Fy value equal to 250 and tensile strength is 410 MPa. Okay, so based on that we can able to find the yield strength and ultimate strength of the section. So this is also given in the code book. Now go and discuss about the limit state design. The limit state are the acceptable member capacities before failure occurs. By designing by this method will assure the structure will safe and will not reach beyond its limit state. The limit states are two types. One is collapse, strength and stability of the structure. Second one is serviceability, deflection under the service load. So we'll discuss about this. We need to check these two serviceability checks in order to achieve the perfect design of the member or structure. Partial safety factor for loads. So what is this partial safety factors? Is generally when you estimate the loads to the structural members, we also can multiply into some factor of safety in order to avoid unexpected loads and make the safe design. That means sometimes our estimation based on, even if it comes to an unexpected loads, the structure can able to withstand those forces. That's why normally most of the course based on the research and practices and expected unexpected loads, they suggest some factor of safety. So this need to be applied during the analysis stage in order to get the ultimate forces. That forces need to be designed. So for example, in IS 800, let's consider about one of the load case. This is the dead load plus live load or crane load. CL is nothing but a crane load. When these load combinations are there, we need to multiply dead load 1.5 times and live load 1.5 times. So that means 1.5 times dead load plus 1.5 times live load. When there is a wind load has been considered, then the dead load will be 1.2, live load will be 1.2, and the wind load is 0.6. So this is the combinations need to be applied. So now let's discuss about the partial safety factor for materials. Similarly, when the structure actually not only due to this geometric imperfection, sometimes there is a material imperfection, and also the member behavior, like some elements are even not even attaining the yield stress, and it actually the local buckling prevents. That means the stresses not even reaching to the yield stress. So that's why if you divided this yield stress into particular safety factor, for example 1.10, that means even when that kind of material is not even reaching to the yield strength, still it is safe to use for the design, because we already reduced the strength 10%. So if any member, like a slender members, not even reaching to the yield point, so that means this safety factor will save the design perfectly. So that's why we use the safety factors for design of the materials. Now deflection limits. So in strength we are going to check the capacities. In deflection we need to see the serviceability check. So serviceability check will be done based on the deflection limits. So we need to find out based on the industrial building or residential building, or what type of the structure we are going to check, and the allowable deflection is span by 150 for an example of live and wind load, purlins and girts, elastic cladding, span by 150. So that means span of the member by 150, and the actual deflections will be calculated based on the analysis. So if actual deflection is less than maximum deflection, that means the structure is safe. So with this, I think we can conclude here, and in the next lesson we will discuss more in the example problems. Thank you.